Hello, everyone. So if you're watching this video, that means that hopefully it's Tuesday. And today we're going to be talking about percentage yield. You've been working on stoichiometry a lot the last week or so and figuring out what to do if you have the amount of one reactant or product, how to figure out a different one that's in the formula. Well, today we're going to start talking about taking those yields and actually putting it into practical situations, okay? I don't know if you remember, but Ella and I had made a demo video that I showed last week where we took some vinegar and baking soda and put it in a balloon, and then we masked it at the end to see how much gas we collected. Well, you should be able to use stoichiometry to make a prediction about how much gas you could make, and then you can do a calculation called percentage yield to actually help you figure out how close did you get. Did you have a good yield? Were you able to collect all of it or most of it? Okay, so we're going to start here with some notes. So get out your science notebook or some rando piece of paper, whatever you're going to take notes on. And we're going to start here with this today. Okay, so this is the definition of percentage yield. It says this is the ratio of actual yield to theoretical yield multiplied by 100. Okay. So it's a ratio of actual to theoretical. Actual will go on the top of the fraction. Theoretical yield goes on the bottom. So let's define those. What does it mean for something to be actual versus theoretical? The theoretical yield, it's the maximum amount of product that is calculated from a given amount of reactant. So the theoretical yield is the one that you're using math to get. That's the stoichiometric amount. So if I ask you, well, what's the theoretical yield for this and this, you would have to do math to figure that out. You're going to have to do some stoichiometry to figure that out. Okay, this is the maximum, like the perfect amount, because it's in theory, theoretically, the perfect amount, the maximum amount would be this. Okay, now the other amount is called the actual yield. What is actual yield? This is the measured amount of product obtained from the reaction. Okay, so the measured amount of product obtained from the reaction. Okay, so this is what, if you go back to the lab and you run the experiment, and let's say, you know, that you're putting baking soda and vinegar in a balloon and you're trying to collect the product or one of the products, which was carbon dioxide gas, the actual amount that you collect in the balloon, that's called your actual yield. Okay, and then to get the percentage yield, you just take your actual divided by your theoretical multiplied by 100. I give this example every year because it's the one that it always makes me think of. If you ever go make cookies like from a mix, or if you could just get one of those big tubes of cookie dough, it may say on there that it should yield, you know, if you do it right, 3 dozen cookies or something like that. Okay, now that's the maximum theoretical yield. That's what somebody has said, that if you make them in these perfect proportions and you do it just right, you should end up with 3 dozen cookies. Now, if you're like me and you take that tube of cookie dough and you eat half of it before you ever get it on the pan, or if you get tired at the end and you just start globbing them all together so you're making cookies that are giant, you actually may end up with producing maybe 12 cookies instead of the predicted 36. So what's your percentage yield? Well, 12 divided by 36 would be about 33%, which is terrible. Like if I was a cook in a kitchen, I would get fired, right? And the same thing goes for chemical engineers. They have to predict how much product they can make if they're working for Pfizer or for Johnson & Johnson and they're trying to make shampoos or medicines. They have to predict how much could they make with this amount of chemicals. And if their percentage yield is not pretty good, they're probably going to be looking for a job. Okay. All right. So what we're going to do now, though, is we are going to go ahead and practice a couple of problems like this. There will be some practice problems assigned after this video that you're going to have to do on your own. So these are just a couple for us to do together. Okay. So it says let's practice. And the problem is written there. Carbon reacts with steam at high temperatures to produce hydrogen and carbon monoxide. Okay. And then it's a 2-part problem. And they give you the first part, and then the second part is going to be the actual percentage yield part. I'm going to skip out of this notes part. I'm going to go to my smartboard right here. Okay, and let's see. So here's that problem. I just wrote it up on my smartboard, and I'm going to go to the smartboard and we're going to do this together. Okay. So it says carbon reacts with steam at high temperatures to produce hydrogen and carbon monoxide. The first thing you're going to have to do is to write the reaction. Okay. So what are your two reactants? Carbon and steam. What is steam? Well, it's water vapor. So H2O. Okay. And it yields to produce hydrogen and carbon monoxide. Well, how do we always write hydrogen gas? It's part of Han and the halogens. So we're going to do hydrogen, H2, and carbon monoxide gas. Carbon monoxide is C and then one oxygen. Okay. So there's our formula. Now, with any kind of chemistry equation, you always really just want to check or make sure it's balanced. Okay. So we'll look at this, just look at it real fast. You have one carbon on each side, two hydrogens on each side, and one oxygen on each side. So it's good. It's balanced. Okay. So let's go ahead and start with question number 1, or part 1. It says, if 2.4 moles of carbon react with excess steam, how many grams of each product are produced? All right. Well, what I'm going to do is I'm going to go ahead and circle my knowns and my unknown. It says if 2.40 moles of carbon. So here's my carbon, and I have 2.40 moles. All right. And it reacts with excess steam. So it says it's reacting with the steam, but you've got plenty of it, so don't worry about it. How many grams of each product? Well, there's 2 products. So I'm going to figure out my grams of this one and my grams of this one, right? All right. So I'm going to work through 2 problems here. Now, the way that I'm going to work this is I'm going to go through the step method. Like I've balanced my equation. I would convert grams to moles if I had any, but I don't have any grams. It's already in moles. Well, the next part is once it's in moles, you just look at the ratio of carbon to one of the unknowns. Okay. So what's the ratio of carbon to hydrogen? What's the mole ratio? In the problem, in the original equation, it's 1 to 1, right? Well, that means if that's the mole ratio, the same thing would apply to the amount that I'm given. So if I have 2.40 moles of carbon here, that means I have 2.40 moles of carbon here, right? Well, now at this point, they're wanting to know how much does that weigh, how many grams is that? Now it just becomes a little conversion problem, right? So you can do it however you want. You can do the factor label method, which is my favorite, but I think a lot of you like the triangle. So I'll go ahead and use the triangle method here. Okay, so I'm just going to convert this 2.40 moles to grams. So moles goes down here in the left, so I'll put 2.40. I'm trying to figure out my grams. I don't know that, but I do know the molar mass of hydrogen, H2. I would look at the periodic table, right? And on the periodic table, 1 hydrogen is 1.01, 2 hydrogens would be 2.02. Okay. So then all we're going to do is multiply. So I've got 2.40 times 2.02. That gives me 4.85 grams. So I have 4.85 grams of hydrogen that get produced from 2.40 moles, okay? Now they're wanting to know the mass of each product, so I'm going to go ahead and do this for my carbon monoxide too, my CO. And again, I'm going to look at my ratio of carbon to carbon monoxide. What's that ratio? It's 1 to 1 again, which means that if I have 2.40 moles of this, I've got the same moles of this. All right. Now I'm just going to convert moles into grams, right? I'm going to do another little triangle here. I'm looking for my grams. I don't know that. I know the moles is 2.4. And I know that the molar mass, I would look at the periodic table. Carbon is 12. Oxygen is about 16. So that'd be around 28 grams per mole. That's the molar mass, right? And then I'm just going to multiply 2.40 times 28. I'm going to get 67.2 grams of carbon monoxide that would get produced. Okay. All right. So now at this point, I've got my answers. I've got my grams of each product produced. So I'm going to go into part 2. It said if you did this lab and actually produced 3.72 grams of hydrogen gas, what was your percentage yield? Okay, so listen, the question that they're asking on this particular problem, this is the main question. What was the percentage yield? Okay, so what we're going to do is look at what they give us. It says we actually produced 3.72 grams of hydrogen gas, right? Okay, so we're looking to find out our percentage yield, which percentage yield, remember, is just actual yield over our theoretical. Actual over theoretical times 100. And here's the thing. I'm going to erase some of this really quick, by the way. This will have some more room. Okay. So here's the deal. If it's actual over theoretical times 100, okay, and we're dealing with hydrogen gas, so we're going to be specifically looking at this one, right? Hydrogen gas. I need to know what my actual amount was that was produced and the theoretical amount. So you've got to go back and ask yourself, well, which one's which? If you think back to what we just talked about with the notes, theoretical, this theoretical mass is the one based on math or based on stoichiometry. So would it be the 3.72 or the 4.85? And it should be the 4.85 because that's the one that was produced, like maximum that was produced from math calculations. Like if everything went perfectly in the lab, it would be 4.85 would be the maximum amount that you could get based on 2.40 moles of carbon, okay? Now the actual amount, they tell you the actual amount produced was 3.72. So actual will go here and then times 100, okay? So our percentage yield, 3.72 divided by 4.85, is going to be around, and then times 100, 76.7% is our yield, which honestly is not great, right? If you worked for Pfizer or Johnson & Johnson, and you were only getting like a 76% yield, I don't know that you wouldn't get a firm talking to, right? You want as close to 100% yield as you can get. So what could cause our percentage yield to be so low? Okay, and it's a couple of things. If you're actually doing the experiment in the lab, just like what Ella and I did last week, there's a possibility that you could let gas escape or that something could spill in the beginning. You could have human error mistakes that could cause the actual yield to not be as great as what you could have predicted. Okay. Also, there could have been a problem with the math. Maybe we did the math wrong in the beginning, and our calculations were off, and we predicted too much. So you would probably want to go back and check a couple of things. But that's how you're going to do percentage yield. Okay. We did a stoichiometry problem first to figure out our products, and then for part 2, we just plugged in our actual yield over our theoretical yield, and then times 100 and got our percent. Okay, so let's do another practice problem. Okay, this is the next one. It says coal gasification is a process that converts coal into methane gas. If this reaction has a percentage yield of 85%, what mass of methane can be obtained from 12.50 grams of carbon? Okay. And so they give us our formula. I'm going to make it a little bit bigger just because I want to be able to balance it if I need to. So I have solid carbon, and it reacts with liquid water to yield methane gas, okay, and carbon dioxide gas. Okay, coal gasification is what you're dealing with. Okay, All right, so we've got those. Let's double check and make sure it's balanced. Okay, you have 1 carbon on each side. We have 4 hydrogens on the product side, so I'm going to make this be 4 on this side. And then I've got, this looks weird, I'm going to fix that. Hold on. 2, yes. Okay. And then I'm going to check my oxygens. I have 2 oxygens on the left side of the equation, and I have 2 oxygens on the right side. Oh, wait, I just noticed my carbons are off, right? My carbons, I have 1 on the left side, but I have 2 because it got split. So I'm going to go ahead and put a 2 right here. So that's good. 2 carbons, 2 carbons, 4 hydrogens, 4 hydrogens. And then look, I have 2 oxygens on the left side because that 2 distributes. And then on the right side, I have 2 oxygens in the CO2. So is it balanced? Yes. Okay. If you're still having trouble with balancing, you need to go find some games online and practice. All right. Okay, so let's read through this problem. If this reaction has a percentage yield of 85%, what mass of methane can be obtained from 1,250 grams of carbon? Yikes, that's a lot of information. Okay, so I'm just going to sort it out and try to figure out what I'm going to do here. They give me a percentage yield, so I'm going to kind of put that over here and set it aside. It's an 85% yield. And I know that with percent yield, that means I've got to have an actual yield over a theoretical, right? And so I've got to figure out what I've got. It says, what mass of methane, which one of these things is methane, do you think? Methane is this one. Okay, so they're asking for what mass of methane can be obtained from 1,250 grams of carbon. Just plain old carbon is this one. We'll have 1,250 grams of carbon. So here's the thing. You've got a lot going on. So it says, what mass of methane can be obtained from 1,250 grams if you had a percentage yield at 85%? So they're telling you they've already done this experiment and they had an 85% yield, okay? So the thing is, we don't actually know the theoretical yield or the actual yield, but can we figure one of those out? And the answer is yes, we can. We can actually figure out both, but we're going to have to do the theoretical before we can figure out the actual, okay? So remember, the theoretical is based on math, and it's based on stoichiometry. So let's do some stoichiometry and figure out how much methane we would predict in a reaction like this, okay? So with this reaction, I'm going to do I'm going to set it up in a direct proportion, a mass to mass direct proportion. Now you could do the step method like what we did a while ago and convert grams to moles, apply the ratio, and then just convert back. But I'm going to do a direct proportion mass to mass ratio, okay? So here we go. I'm going to set it up using my known over my unknown. So I've got my new information tells me that I've got 1,250 grams of carbon, right? Over, I'm looking for my X grams of CH4. That's my new information. So I need to find out what was the original information. What were my original masses in the problem? How much total carbon did I have in the first place? Well, if you look here, you're just going to take 2 times whatever carbon's molar mass is. So you need your periodic table. If you find carbon, carbon is 12.01, and then we're going to double it. So it's going to be about 24.02 grams of carbon over. And then look at this side. I have 1 mole of methane. So I'm just going to do carbon plus 4 hydrogens. So 12 plus 4, basically, is about 16 grams of methane. Okay. And I'm just going to set those sides equal to each other, right? And then I'm going to use my calculator and I'm going to cross multiply and solve for x. Okay. All right. So here we go. I've got 16 times 1250. And I come out with 20,000. And I'm going to set that equal to 24.02x. Okay. So now I'm going to take and solve for x, 20,000 divided by 24.02. So x equals 800, and let's see, I've got 4 digits. Let's do 832.6 what? You've got to have a unit, 832.6 what? It's grams of methane. Okay? So we're making a prediction and saying with 1,250 grams of carbon to start with, I think that we could probably make around 832.6 grams of methane. That's what we're predicting under great conditions, under perfect conditions. That's the maximum amount that we're going to be able to produce, theoretically, right? So we're going to take that number, that 832.6, and we're going to plug it in right here in the theoretical spot. 832.6, okay? So then I'm just going to take this and solve to find my actual. Now, in a situation like this, you've got this 100 right here. You really need to get rid of it, right? So I'm just going to divide both sides by 100. So it's going to make my equation look like this. And again, I'm going to erase a little bit just so I've got some room to work here. So I'm going to take my 85 divided by 100 first, okay? So it's going to make it look like this. I've got 0.85 is equal to actual yield over 832.6. And now at this point, that looks like something we can solve, right? Okay, so I'm just going to cross multiply. You know, this would be like over 1. Cross multiply, solve for x. So I'm going to take 0.85 times 832.6. So my actual yield, what we got in the lab when we did this experiment, was around 707.7, as long as 7 grams of methane. That's what we actually produced in the lab, okay, in order to achieve that 85% yield. That's what they got whenever they did the lab, okay? All right, so again, actual yield is what you get in the lab. It's the measured amount. Theoretical yield is based on numbers. It's based on stoichiometry, and it's under perfect conditions, like no human error. This is what we predict that we could get, okay? So that's what we're going to be practicing. That's going to be what your practice problems are over. Okay. Good luck. I hope it goes well for you. Let me know if you need help.